Okay, in this video, we're going to continue our discussion of residence time distributions, and we're going to talk now about pulse and step experiments that are used to determine residence time distributions. So basically, a residence time distribution is measured by dosing a tracer to the reactor. So if we have a reactor, so I'm just going to kind of draw a reactor. This could be any reactor. Here's our reactor. We have our feed coming in, and we have the stuff coming out. And what we do is we inject tracer at the feed, and then at the outlet we have a detector where we measure the concentration coming out. So we know the concentration that goes in. We measure concentration coming out as a function of time. So what is a tracer? A tracer is non-reactive because we want to be able to capture it, so we need to know how long our tracer spent inside the reactor, and it's hard to do that if we allow our tracer to react. So it's a non-reactive material. It's easily detectable, so I have to be able to detect it in my detector. It has physical properties that are similar to the reactant mixture. And is completely soluble in the reactant mixture. This is so that it can be representative of the reactant product mixture. It's often a colored material, maybe a radioactive material, an inert gas, something like that. It can be dosed in either a pulse or a step experiment. In a pulse experiment, an amount of tracer is suddenly injected in one shot. So if we go back to our diagram here, basically in a pulse we would inject just one dose of that and then stop dosing. So we have one dose of that at some concentration is dosed or is injected, and then we wait for that concentration to come out in the detector. So when we do that, the time needed to collect all of that tracer is used to determine the residence time distribution. So we can kind of draw that. So if we talk about, let me draw that a little bit differently. So we'll say let's say at reactor inlet, we could have a plot of concentration versus time, and what we would see, we would just kind of do one dose of concentration, and then at the reactor outlet we'd get something a little broader, so stuff coming out in more of a distribution. And that shows us that we have residence time distribution. Everything entered in a very small amount of time over here But then it took things longer, or some things shorter and some things longer amount of time to come out. So this is if we're measuring this at the reactor inlet and outlet. That's a pulse experiment. So we've dosed one pulse of material. In a step experiment, a concentration is constantly fed. It's constantly fed to the reactor. I guess one thing I could attempt to do here is give myself more room. So let's see here. Oops. All right. Step experiment, a concentration of tracer is constantly fed to the reactor. So if we wanted to draw the same plots at the reactor inlet, I didn't give myself enough room there either, so I'm gonna concentration versus time. Basically in a step, I have like nothing, 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 and then all of a sudden I start, and then I'm going to dose a constant concentration. And what's going to happen at the reactor outlet? I'm going to have kind of a similar shape, but it's not going to be as perfect, and the reason for that is because the different molecules spend a different amount of time in the reactor, and henceforth I'm going to get some spending a little bit less time than others, and some spending a little bit more. Let's see here. So what this step experiment is, my concentration coming in, function of T, is going to be equal to 0 for t less than 0, and it's going to be equal to c naught for t greater than or equal to 0. That's different than in my pulse experiment, where I basically have some concentration dosed to the, or injected into the reactor, and then I stop. Okay, so the time needed for the concentration of tracer to exit the reactor and equal that entered. So basically the amount of time it takes for me to collect all the tracer that entered, that is what helps us determine the residence time distribution. So some important quantities: delta n, that's the amount of tracer leaving the reactor between time t and time t and time delta t. I can get this by doing like kind of a mass balance on my tracer. So if I have some concentration leaving the reactor, they'll call that C of T. This is from the C of T curve at the reactor outlet. So this is what I'm collecting. So I'm collecting this concentration at the outlet. I can multiply that by my volumetric flow rate, and then delta T, the amount of time I collected it in. That is the amount that leaves in a certain time window. If I divide that by the total amount that was fed, that gives me the fraction of tracer that has a residence time between time t and delta t. So I'd say delta n divided by n naught is equal to the volumetric flow rate times C of T times delta T divided by n naught. So n naught is the total amount that was ejected, and it's equal to the integral from 0 to infinity of the volumetric flow rate times C of T dt. So basically it's going to give me the total number of moles of tracer that were collected, which if I integrate between time equals 0 and time equals infinity, that should give me the total number of moles of tracer that were injected. Okay, the residence time distribution, we're going to denote that E of t. Sometimes it's also called P of t, lowercase p of t. We're going to call it E of t. That is going to be the fraction of tracer that exits per time, so per time interval. So we would say delta n over n naught. That's going to give the fraction of tracer that exits in a time window divided by that time window. That's going to give us our residence time distribution. So we can write that down. We would say that's equal to the volumetric flow rate times C of t times delta t divided by NO and then delta t, and that's going to give us the volumetric flow rate times C of t divided by N naught. What that's going to give us is the volumetric flow rate times C of t divided by the integral from 0 to infinity of the volumetric flow rate times C of t dt, based on our definition of, well, not our definition, but what has to be true about the amount of tracer that enters. And so then we have this expression here, and if our volumetric flow rate is constant, what this gives us is E of t is equal to C of t divided by the integral from 0 to infinity of C of t dt. So that's going to give us our residence time distribution. If we want, we can now use this E of t curve, this residence time distribution, to determine the fraction of tracer, and hence reactor contents, that leave the reactor after having resided in the reactor for some amount of time. So for example, if we want to know the amount of reactor contents that reside in the reactor between time 1 and 2, we can integrate the residence time distribution in between that T1 and T2. If we want to know, since the residence time distribution is basically a probability, that tells us that if we sum up all of the residence time distribution from 0 into infinity, we should get 1. So by definition, the integral of the residence time distribution between t equals 0 and t equals infinity is equal to 1. So in other words, all of the tracer must come out. Other properties of interest are the cumulative distribution function, f of t. F of t is equal to the integral between 0 and t of E of t dt. And it tells us the fraction of tracer or reactor contents exiting that has been in the reactor for less than time t. Another important one is the mean residence time. So for example, CSTRs and PFRs operate at their mean residence times. That's why we just have one residence time when we talk about ideal CSTRs, PFRs. Other reactors, or real reactors with imperfect mixing, also have mean residence time, but the mean residence time is not descriptive of the reactor as a whole. So whereas the mean residence time can be used as a surrogate for the residence time, for the distribution of residence times within a ideal CSTR or PFR, that is not the case for a real reactor. We can find the mean residence time by doing essentially the integral of time times the residence time distribution, dt, divided by the integral of the residence time distribution, dt, This is, of course, equal to 1 by definition. And so this gives us the integral of from 0 to infinity of t times the residence time distribution. And then if we want to know the variance, which tells us something about the spread and the data, basically what we can do there is integrate over between t equals 0 and t to infinity, t minus tm squared times the residence time distribution dt. So these are some of the functions that we're going to be using as we explore residence time distributions.